the Artificial Intelligence Lab at Nokia Bell Labs in Paris, in France. Is currently driving the research activity that is related to the development of 5G and beyond technology, and is especially focusing on the application of reinforcement learning for L2 and L3. Alvaro has as well like a very vast and wide background that covers LTE, cellular network, small cell, computational electromagnetics, optimization algorithm, and satellite communication as well. So without further ado, I think you will enjoy his talk, and I give the floor to Alvaro. Let me move your presentation right, and 1 second. And I guess, Alvaro, you are now able to share your screen.
Okay. Thank you, Lorenzo.
Yeah.
Thank you, Christos. So thank you everybody for the invitation. Thank you also for the nice introduction. I hope I can live up to it. I hope everybody is finding these online lectures useful and interesting. And maybe for the first lecture of the morning, I thought I would begin telling you a story. This is a personal story, so I thought it could be fun. This is something that happened to me a few years back. It was actually a pretty hot summer day in Naples, in Italy. And the occasion was the 2016 Small Cell Blackfest. This was an event organized by Etsy. And this was a sort of interoperability event where vendors of telecommunications equipment get together and they connect their equipment, the devices, in order to try to make them work together. So I had brought my own equipment, which was a very small LTE small cell. And I was about to test a handover from my cell towards the cell of a second vendor and through the core network of a third vendor. So what will go wrong? So we basically put the phone in the shielded box, we program the attenuators, and we begin the test. The phone actually never reached the target cell, and the reason is that my equipment had used 20 bits for the inode BID, when the core network was expecting 28 bits. Now, this was not, as some of you may think, a stupid bug. This was actually not against the standardized protocol, because the standard supports actually both 20 and 28 bits. So, but then this rose the question to me back in the day of why is this ambiguity built into the standard? And the fact is that despite the massive efforts that we put into standardizing protocols are very often used as a holy book, and they're therefore subject to interpretation by the hardware vendors that use them. But if they are actually a holy book, should we rely on humans to write it? And what is a protocol, nevertheless? So a protocol is basically a sequence of messages that two parties exchange in order to fulfill some task. In our case, the task was to transmit user data. We humans, we also use some relaxed concept of protocol, right, to achieve some task. I mean, for instance, if you want to buy a jacket, you go to the shop, and before you actually put the money on the table, you need to have a discussion with the shop owner, right? You specify what you want. You say, I want the jacket. And you say what size, what color. And it's only at the very end of this exchange of messages that you put the money on the table, you get your jacket, and you achieve your goal. Now, this is a very simple example of a human protocol, but as we all know, machine protocols are also not that different, right? So, for example, if the user equipment wants to transmit an uplink message in a 5G cell, for instance, it can't just begin transmitting straight away. It needs first to have a negotiation with the base station about the conditions that we need to respect in order to do that transmission. First of all, the UE needs to request the scheduling resources. It needs to inform the base station of how much data it wants to transmit. And once again, it's only at the very end of this negotiation that the user is allowed to transmit its data, which is what it wants to do. And if there are several UEs in the cell, the base station needs to carry out several conversations in parallel with each and all of these UEs. And conversation is probably the right word here, because protocols can also be thought of as a language between machines. But why do we use this very precise, this very specific sequence of messages? Why do we send a scheduling request, then a buffer status report, and then transmit the data? Why not in other order? Why not other information? Now, as you all know, the industry puts, there are large standardization efforts made every year to get these protocols right. In fact, most large telecommunications companies, they send every year plenty of delegates to standardization meetings, and that's pretty much how protocols are made. They are negotiated. But, and this, I like to ask this question, is this the only way to agree on a protocol? What about the protocol that we all use every day, human language? Now, human language was certainly not agreed in some standardization meeting during the late Paleolithic, right? So it's not like the Neanderthals had a very small delegation and they couldn't push the changes through. So how did human language come to be? Now, this is still a big unanswered question in science, and we sort of know that human language evolved from some proto-language over time, but the details of when and how that happened are still a big question mark. Could our communication protocols also evolve in a similar manner? Could network nodes, like a base station and a user equipment, develop a protocol of their own to achieve the goals that we choose for them? In other words, could two radio nodes learn a yet unknown communication protocol that solves the channel access problem and that is perhaps even more efficient than human design protocols? That's the question I'm interested in addressing here. How do we do it? I apply a technique called multi-agent reinforcement learning, and also recent results from a hot research arena called learning to communicate. And this was what follows. What we do is basically we take a protocol stack at two nodes, for instance, a user equipment, database station, then we replace the MAC layer in its entirety by some sort of intelligent agent. It could be a neural network, it could be some sort of tabular approach as well. And then we let these two sort of intelligent nodes exchange random utterances from some fixed size vocabulary. Now, at the beginning, these exchanges are going to be completely random, but as time goes by and as we train the system, the expectation is that this gibberish will evolve into something meaningful, something that will have an effect on the actions of the receiving node. But how do we detect that a protocol is emerging? I mean, you have to remember that the whole purpose of these protocols is not actually just to exchange messages per se. What we're going to do is we're going to transmit data, either in the uplink or in the downlink. So that's the final goal, that's the task. So when we evaluate performance, we have to evaluate performance in terms of how well are we actually achieving that goal of transmitting user data. We can evaluate it in terms of bit rates, delay budgets, you name it. And perhaps it could be that performance increases not because we have found a better protocol, but perhaps performance increases just because nodes have found a better resource allocation algorithm or a better channel access policy, regardless of the protocol. So how can we evaluate, how can we measure whether the protocol that is emerging is actually contributing to increasing the performance that we see? To do that, we have to define new metrics that evaluate the effect that messages have on the actions at the receiving node. This is typically done using metrics based on the mutual information that helps us compare the statistics between the distribution of the messages and distribution of the actions taken at the receiving ends. Fortunately, these algorithms are very slow. They are very data hungry, It usually takes billions of time steps for this gibberish to evolve into something useful. And that's also why we need the best, the most powerful, and probably also the most expensive equipment in order to run these sorts of training sessions. And I also think that this is perhaps one of the reasons why most of this research today is done mostly at the industry rather than at universities. That's because you need a bunch of money to get these systems running. Why do we want to do that? Well, I think the first reason is pretty easy for everyone to understand. It's money. So why do we want to spend millions of euros standardizing protocols when machines can develop their own? There's also a question of performance. Why should we trust unreliable apes like ourselves to build the protocols that our networks rely so much on, when machines could perhaps do a finer job? And ultimately, there are also scientific reasons to pursue this type of research. You could ask the questions of whether machines will machines ever develop their own language. If they do, then I say that we better have the tools in place to understand what they're saying. And this is not just for knowledge per se, but it also has some practical applications in tasks like fault detection or just to measure performance. The thing is that if we don't know what machines are saying, we may not even know what we're missing. So this is roughly a high-level description of the type of research that we are carrying out at my current research group in Nokia Bell Labs, France. I said it at a high level because I've been told I should not presume machine learning expertise on the audience, which is also part of the reason why I have included a few slides giving you the basics on machine learning algorithms, which I hope will be useful for the other presentations for the rest of the day. And I will show you also 2 or 3 examples of how you can apply machine learning algorithms to some well-known problems in telecommunications. So let's begin with the basics, if that's okay. For those of you who are familiar with machine learning, sorry to bother you, but I also hope that it's sometimes interesting to review the basics from your expert knowledge at this stage. So what's machine learning? I mean, machine learning is basically a collection of algorithms whose performance improves with experience. Okay, so an algorithm is basically an input, a mapping from inputs to outputs. It's just that this mapping evolves with experience. So the longer the history that you have been using this machine learning algorithm, the more this mapping will change. And a machine learning system has several parts. Typically, we begin with some unknown function. This function could be, it could calculate the value of the next action to take, or the expectation of some KPI for some combination of parameters, maybe. And typically, we also have some sort of training data. That's pretty much the basic building block of machine learning algorithms. You need data to train these algorithms. And since the target function is known, we also need some sort of parametric model. That's something that we will use to approximate the function that we don't know. And we do that. We train this model using the data. How do we do it? How do we modify this model using the data? Well, to do that, we need a learning algorithm. I will show you later the basic types of machine learning algorithms. But this is basically some sort of regression technique that helps us make the model fit the data as best as possible, as best as we can. After this learning process, which we call training, we end up with a trained model. That's a model that, if you evaluate on the training data, will perform with a very high performance. Because after all, you've used this very same data to train it. But this is unfair. This is not how you would actually evaluate your model. You wouldn't. It's unfair if you just display the performance of your model on the very same data you've used for training it. That's why in machine learning, performance is typically measured on data that the model has never seen before. That's why we make this differentiation between training and test data. So if somebody gives you a large data set, typically you would split this data set. Typical split is 80-20%. So you would use 80% of your data sets for training, but after training, you just evaluate the performance on your model on the remaining 20% of data that you have not yet used. And some people even go one step further and divide the data sets into 3 parts. You will have the training, the validation, and the test set. And you could use the validation test set, data set to optimize the parameters of your model. And you will be finally, once again, showcasing the performance on your model on the yet unseen test data set. Okay, so when should we be using or not using machine learning? For this, we typically ask a series of questions. The first one is, do we have a model? Well, this depends, of course, on the problem we're trying to solve. Let's say that we're talking about data transmission. Do we have a model for data transmission? The answer is yes. Then we should ask the next question. Do we have an algorithm to implement this model? If the answer is once again yes, then this begs the question of, okay, is this algorithm implementable in a cost-effective manner? In other words, is the algorithm complex? If the answer is no, I mean, if it's simple, if you can build it easily, well, bad news. There's no need absolutely for machine learning. You already have a model, you have a solution, and it turns out the solution is cheap. Why would you want to use machine learning? You don't need it. If, however, you don't have a model, or things change, then you should be asking, do we have data? But if you don't have data, once again, too bad. No need much. You cannot do machine learning. You need data to train machine learning models. And the same goes, if you have data, then you can try it. Once again, even if you had a model but you had no algorithm, you would be asking the data question all the time. And the same goes for complexity. So basically, if you're in this situation, machine learning will let you do things you could not do before. I mean, if you're in a situation where you don't have a model or you don't have an algorithm, well, maybe it's worth to try machine learning because there's nothing left to try. If on the other hand, you have already an algorithm, but it was perhaps too complex, then you may consider trying machine learning because it might provide some better performance than your previous algorithms. But this is really up to your use case. If your algorithm was already delivering high performance, then yeah, maybe there's not much gain to be obtained from machine learning algorithms. So considering all of this, what can machine learning do for communication systems? Well, for starters, it can make implementation a lot simpler. If you think of how we build communication systems today, you will notice that they are basically a long chain of blocks, of processing blocks. If you look at the physical layer of any transmission system, it's basically a long chain. So you get bits in the input, then you code these bits, you map them to symbol, you scramble them, you code them again. So there's a sequence of steps that you need to apply. And each of these steps is one big function block. With machine learning, you could just replace all of these blocks by one major machine learning trainable block that will do all this job for you. And this is a lot easier to implement. Machine learning could perhaps deliver higher performance than we currently have. Typically, machine learning, the more data you have, the higher the gains. So you just need to keep on training your algorithm, just train it like there's no tomorrow until performance gets as high as you want. Very often we have some theoretical models for a problem, but we cannot actually reach these theoretical boundaries. So machine learning algorithms may not provide an explanation for why we can't bridge the gap, but they might be able to bridge the gap. So that's also one feature of them. Very interestingly, machine learning algorithms may let you do things that you could not do before. Maybe some of you have seen the so-called deep fakes. These are these very funny videos you can find on YouTube where some famous person speaks and they say something that they never actually said. Those videos have actually been completely generated by artificial intelligence systems. There's even a very nice website called This Person Doesn't Exist. So you have seen it, but if you go to this website, this website will show you photographs, random photographs of seemingly real people. But actually, all of those photographs have been generated by a neural network. They are not photographs of real people, but they look like that. And the technology behind these deepfakes and these fake photographs is called GAN. GAN stands for Generative Adversarial Networks. These are neural networks that have been trained to produce at its output distributions with the same statistics as the data they have been trained on. We train these neural networks on photographs of real people, and then you just feed it with noise, and it will generate what on the surface looks like real photographs, even though they are not real photographs. And these GANs, these adversarial networks, have been recently applied also to communication systems. I've seen some papers of people who have trained GANs on some channel measurements. They have used them to recreate channel models with very high accuracy. So you will have very realistic GAN-generated channel models that you can use in your simulations or even in your deployment tests. So this is something you could not do before. Typically, one would use some sort of channel emulator, but things might be changing there, and channel models based on GANs might be the future of network simulation. Machine learning may also let you do things a bit better than before. Think of image recognition. We have image recognition for 30, 40 years, but everything has been rewritten in the last 10 years since people began using neural networks for image recognition. And as I said at the beginning, you could just replace a long chain of blocks by one large machine learning algorithm. Now, this is, I've just described more or less what machine learning can do for you. But what are the showstoppers? What's difficult? Well, the first thing is, how do you get data? Fortunately, in telecommunication systems, we can produce lots of data relatively easily. Things of the physical layer or the map layer. Those are systems that take decisions every millisecond, which means you can produce lots of data very rapidly. So it's typically easy in communication systems to produce data, to feed machine learning algorithms. What's difficult is inference. In machine learning, we typically have two use cases. I spoke to you about the training of machine learning algorithm, but after you have a trained model, you have to use it. When you use a trained model, we call this inference. And inference is usually a lot faster than training, because training involves processing a lot of data. And typically, you want to do inference at the speeds comparable to those of the physical layer. That's itself also hard. The physical layer needs to perform calculations very fast, take a lot of decisions every millisecond. And if you have to run a large neural network every millisecond or every fraction of a millisecond, that might not be possible in portable platforms. That's why most machine learning algorithms today are still run in the cloud. And then comes the questions of whether you can have hardware accelerators also on portable platforms. There's also this challenge of online learning. Online learning refers to algorithms that can perform inference and training as they go. So at the same time that you use them, they train themselves. Before I separated the phases of training an algorithm and using it through inference. So here by online learning, we're talking about doing both things pretty much at the same time. And this is a challenge because typically one disadvantage that you have of using trained algorithms is that after they're trained, their behavior doesn't change anymore. So they cannot exploit new experiences collected through usage. That's why there's a need for algorithms that can be trained in the field. Fortunately, this has unexpected outcomes where you don't know what the result of the training is going to be. So in terms of deploying such online learning algorithms to customer-held devices, there's currently a big opposition to doing that because it's quite unclear how these devices would behave in the field. And finally, there's, as I said already at the beginning, running these algorithms is costly. You need high computing platforms. So it's in cost, the compromise between cost and benefits is usually something to be considered before deploying machine learning algorithms to the customers. Okay. So that was sort of the high-level introduction to machine learning. Now I'd like to get maybe a bit more concrete. The first and most basic type of machine learning algorithm is called supervised learning. This is mostly a category of algorithms. What we're trying to do is just to predict outputs of a function after having observed some input and output mappings. And here I give you a very simplistic example where you see we have some data, and the data maps the CQI to some data rate. CQI is the so-called channel quality indicator. It's a measurement of the channel quality that most UEs measure continuously, and they report back to the base station. The better a channel is, the higher the data rate you get. Well, at least typically that's the case. So in this particular problem, what we want to do is try to predict the data rate that a user will experience considering the CQI it's currently measuring. And we have some data to do that, and I put the data here. And you may think that this is a very trivial problem. You could just apply some simplistic linear regression technique. You could just draw a straight line through the data and use that to predict future outcomes. And you could even go one step further and use a polynomial of whichever order you want. And yes, you could use linear regression to solve this fitting problem. However, linear regression has some downsides. For starters, it typically needs to inverse a large matrix. So here I'm just showing you a handful of points, but if you had millions of data points, this becomes undoable using typical normal equation. The normal equation is a typical linear regression technique. In the same manner, I believe the normal equation only works for one-dimensional data. So if you had multi-dimensional data, you wouldn't be able to do it. So how do we do that? For instance, here I'm showing you another example of multi-dimensional data. Here, I've just expanded the previous data sets with more columns. Okay, so now for every target, that is for every data rate measurement, now we know a lot more than just the CQI. Turns out that for the first data point, that's the first row in this table, we know that for the CQI1, now we know what modulation encoding scheme the user was using, how many TTIs it was transmitting for, how many resource blocks in the frequency domain it got allocated. We also know its rank indicator, its precoding matrix indicator, and ultimately its CQI. And we want to, considering all of these inputs, we want to predict the data rate. How can we do that? Well, you could once again define a linear model on each of these features. If you wanted some nonlinearity, you could even add nonlinear features. Think of it as adding more columns artificially created to this table. That would be those columns, where those new columns could include the power of 2 of the initial data, or the power of 3. You can add as many higher order terms as you wanted, and still have a linear model on it. For instance, here I'm showing you a simple linear model where I just multiply the inputs, that's the X vector, by some parameters, which I've called theta here. So theta is a vector containing all the parameters of our model. Now, these parameters are not known at the beginning, but this model is a linear model of the data that we have, that we use to predict the data rate. How do we find the values of the theta parameters? By the way, one downside to these online presentations, I don't have visual feedback on how the audience look. I don't know if they look puzzled or they're completely lost, or so if those of you can comment, I will elaborate if things are unclear.
I think you are very clear, Alvaro. I'm eating a focaccia. So I'm enjoying your lesson with a focaccia.
That's the right way to enjoy it.
Yeah.
Okay. So I had just introduced to you the model. Maybe I'm going to use the highlighter here. Okay. So this is the model that we're going to use to model the data. And what we want to do now is to find the values for this parameter of vectors. These parameters we don't know. So what we do is we define this error function, which is basically an error function, that's the quadratic error between the prediction of our model and the data that we have. That's this column here. Okay, so once we have defined this error function, we can justify the cost function by computing the average over all of these samples that we have. Here we have the samples in the rows. And as I said, this data set can be very large. We have hundreds of thousands of data samples. By defining the cost function this way, now we can evaluate whether our model is better or worse depending on how high this cost function is. Now, it's important to notice that this cost function is only a function of theta. Okay? It's not a function of the data. So it's differentiable only on theta. So we basically converted a linear regression problem into an optimization problem. Because what we want to do now is to find the theta that minimizes this cost function. And then we can apply any optimization algorithm that we want to do that. Typically, in machine learning, we use gradient descent, which is being known for a while. Here I'm showing you a simplistic illustration of how this cost function would look like. Imagine that we have a very simple linear model with only two parameters. Okay, so I said before that we have this theta vector, which is a large vector with, sorry for my handwriting, but it's hard with the mouse. I hope this is more or less clear. So we have a vector theta with two parameters, with two elements. And here I show you the cost function in 2D, which is basically a valley of peaks, a landscape of valleys and peaks with highs. That's the combination of theta parameters with high error, and valleys. That's the combination of theta parameters with very low error. So what we want to do is to find the combination of theta parameters that have the lowest cost. So we basically begin at some random location that we choose, and then we iterate by applying gradient descent on this combination of theta parameters. Now, the gradient of this theta function only gives you the direction of descent. That's why you also need another parameter called the step size, which is here. It's also called the learning rate. Okay, so we differentiate the cost function and we multiply it by the step size. And it's important to notice that by doing this repeatedly, we take steps always in the direction of the falling slope. And in the end, you will see that I've plotted here, by doing this over several thousand iterations, that the cost function decreases until at some point it doesn't decrease anymore. You need to have reached the minimum cost combination. So at that point, you have a trained model. You have found the parameters of your model, and you can use it to test it on the test data you have previously saved. So that's pretty much the basics of supervised learning. Not much of a mystery here, I hope. Then we arrive at deep learning. Now, previously I've shown you a very simplistic linear model that we could use, but unfortunately the world is not linear. Okay, I think of, I don't know, gravity, or the way with which light intensity decays with space, or just the frequency range in your ears. I mean, they're all non-linear events. So how do we model these non-linearities What type of models could we use to model nonlinearities? We could certainly continue to use polynomial approximators and introduce nonlinear features. We could introduce high order powers or just logarithms in your linear models, trigonometric models. But what if there was a generic function that could model any nonlinearity? Well, there is one, and that's a neural network. So a neural network, an artificial neural network, is nothing more than a math construct. Okay, it's a function, it's a mathematical function. And it's basically a combination of so-called neurons, which are basically a small mathematical function. Okay, so if you look here, this is just one neuron of a neural network. And this neuron is called a neuron, but it's actually a mathematical function. Okay, it receives inputs and it produces an output based on those inputs. And the output looks always the same. It's the application of a G function, which is called the activation function, over some linear combination of the inputs, right? And typically we introduce a bias term, which is typically set to 1. So basically you introduce numbers, you multiply those numbers by some theta, and then you apply an activation function G. Now, why do we need this activation function? Well, we need it because that's how you can model nonlinearities. These linear functions are typically nonlinear, and there are many activation functions you can use. I've illustrated here just two. Here I have the sigmoid activation function that you see clearly nonlinear. But actually, one has to admit that ReLU is the most widely used activation function today. ReLU stands for rectified linear unit, and it's basically a function that just eliminates the negative, sets to zero the values of sets to zero the outputs when the inputs are negative. Okay, so if the result of this linear multiplication is positive, you get at the output the same things as you get in the input. And that's just what one neuron does. And if you combine many of these neurons, typically one would stack them in layers. I've shown here in the left, and then you chain these layers one after the other, then you can model very complex mathematical functions. In fact, it has been proven mathematically that neural networks are generic function approximators. You can use them to model any function that you like. So whichever nonlinearity you have, it can be modeled by a neural network. It's just a question of how big the network needs to be. And by big, I mean how many layers it needs and how many neurons do you need in each layer. Okay, so by the way, I'm going fast through the basics of reinforcement of machine learning. I don't want to go with my detailing. I want to jump quickly into the application of machine learning to telecommunication problems, but I still needed to introduce these concepts. So hopefully it should be.
Sounds perfect.
Should be finished soon.
Yeah.
So I've shown you machine learning. I've shown you deep learning. Now I want to give you a primer on reinforcement learning. That's yet another paradigm of machine learning. Reinforcement learning is basically learning what to do. By learning what to do, I mean is how do we map situations to actions? That's precisely doing something, right? You are in a situation and you take an action, you take a decision. How do we do that? Well, typically you just try actions randomly and you see which ones yield the most reward for you in the long term. So in reinforcement learning problems are typically modeled with two parts. There's an agent that takes those decisions, that takes those actions, and there's an environment, which is an abstraction on the problem you're working with. And these are problems that have some sort of built-in sequential decision making, right? So there's a time stepping, and on every time step, this agent has to take a decision, has to execute an action. And this action has an effect on the environment. And at the same time, the agent also takes two measurements from the environment. One measurement, which we call the state, which puts the agent into context regarding what are the current conditions. and another metric which we call the reward, which is a sort of evaluation on whether the past action was good or bad. Okay, so think of it as some sort of pleasure metric. And the goal of the agent is to maximize the reward it obtains over time. And that's why it's also important to define this quantity called the return, which is nothing more than the addition, okay, of the rewards one obtains over time. Okay, so in the first time step, we obtain this reward. Second time step, we obtain this other reward, and this goes on. You add them all together, and this is the return at the original time step. Now, this equation is, you see that in this equation, you see that we are multiplying the rewards by some gamma factor. This is called the discount factor. This is just there to highlight the fact that rewards are more worth to us in the present than in the future. Okay, so if I'm going to give you €1,000,000 today, €1,000,000 is worth more today than it is 1 year from today. So there's a decay, a loss of value over time. And that's what this discount factor models. But you don't need always a discount factor in all problems. So if you don't need it, you can just set it to 1. And at the end of the day, this return collapses into just one large addition of rewards. Okay, so this interaction between the agent and the environment is typically modeled as a Markov decision process. NDPs for short. NDPs are known since the 50s, and they basically are a way of modeling sequential decision-making problems. Markov processes, they have a property called the Markovian property, which states that future states only depend on the current state and not on the previous ones. And this is somehow a bit of a tongue twister, but it's important. Think of chess, for those of you who are familiar with chess. Maybe. So if you think as the state of a chess problem, as the position of the pieces on the board, that's all the information you need to play the game from that position onwards. It doesn't really matter how the pieces got to the places where they are now. The past doesn't matter. All that matters is the state, the current state. That's all you need to behave optimally in the future. And that's an important property of Markov decision process, this Markovian property. This is not true for all problems. There are some problems that have correlations between consecutive states, so they break this condition. So you could not model them as MTPs. Although there are some approaches to solving this. Typically, you could have maybe a window of past states that will help you disambiguate those correlated sequential states. Now, what does this intelligent agent do? As I said that on every time step, the agent takes an action. The agent begins in an initial state, it takes an action, receives a reward, and it reaches a new state. And then this begins all over again. How does the agent decide which action to take? Well, it follows a so-called policy. Policy is a mapping between two states and actions. Okay, so it's a function whose input is the state and whose output is the action or a distribution over the actions. Of course, the challenge lies in the fact that this policy is typically unknown when you begin the problem. So you have to learn through interaction with the environment. And to do that, we have to define two other important magnitudes in deep learning, in reinforcement learning. The first one is the so-called value function. Okay, the value function under a given policy is the expectation over the return. Okay, I defined the return before as the addition of the future rewards, and the expected return you would get at a given state is what we call the value function. That this is a function that gives you the value of a state, and it measures how desirable that state is. States with high value means that those are states where you should expect to have a higher return going forward. Similarly, you can also define the so-called action value function, which is a generalization of the value function over a combination of state and action. It's again the expected return for a given state and action. That means if you are in a given state and you take action A, this action value function tells you what's the return you should expect. And these action value functions are typically called Q functions. That's the most common term. Please remember that because it's going to be important in the next slides. This is the Q function. And now that we have this definition of value functions and actual value functions, these functions define an ordering between policies, because now we can compare policies. We can say that one policy is better than another policy if the value function of the first policy is higher than the value function of the second policy for all states. Okay? That's again computed, but mathematically it can be expressed very simply. And it basically allows us to decide whether some policies are better than others. And considering this, we can conclude easily that there's always one optimal policy. That's one policy that is at least as good as all other policies, typically better. And one interesting conclusion also is that optimal policies are not necessarily unique. Sometimes there are many optimal policies. It's just that they all have the same value function, even though the policies will be different. I fear this is too much information for one slide, but yeah, I'll let it sink in, and hopefully you guys can review it later. The last important and basic concept of reinforcement learning is so-called Bellman's principle of optimality, which basically says that, which basically is an equation that relates the value function at a state in terms of the value function in future states. And this already provides hints towards dynamic programming on how to build this algorithm. Okay, this is the Bellman equation for the value function and the policy pi. And I think it's a nice exercise to try to write the Bellman equation for the Q function that I showed you before. Okay, so I leave this up to you for your free time. But just remember that this equation shows you the relation between the value of a state and the value of the subsequent states. Okay, so now we arrive at what's probably the most important reinforcement learning algorithm, which was developed at the end of the 80s. And this is so-called control algorithm. By control, we typically differentiate between control and prediction algorithms. In prediction algorithms, we're giving a policy, and the goal is to measure the expected total reward from any state given that policy. And in control algorithms, the goal is to actually find the optimal policy. And Q-learning is a control algorithm. So what Q-learning does is it tries to find and discover by sufficient interactions with the environment the Q value function, the Q function. So what it does using a tabular method, it stores in memory a very large table of all the states and actions, all possible states and actions of your problem. And at each of those combinations, it stores the Q function. Now this table is initialized randomly, contains just rubbish. But as the agent interacts with the environment and takes decisions, which are usually random at the beginning, it updates the entries in this table. And the algorithm is pretty simple. And this is proven to converge to the optimal Q function. So after several thousand iterations with the environment, the values written in this table will provide to you the values of each state and action combination. And that's all you need to find the optimal policy, because if you know the value of the actions on a given state, well, then it's pretty clear that the optimal policy is just to choose the action with the highest Q. Okay, so we just choose the action with the highest value. And once again, in this machine learning algorithm, we also have this alpha parameter that I showed you in the gradient descent slide that expresses how big a step we're taking when we update this table. One important property of Q-learning is that this is a so-called off-policy algorithm. That's because the agent does not necessarily need to follow the policy dictated by Q. All it needs to do is to generate the state transitions by interacting with the environment. But it doesn't need to follow the optimal policy precisely because it doesn't know it. But it doesn't matter. In the end, this table will converge to the optimal policy. Okay, now fast forward to 2013, which is the year when the DQM paper was published in Nature magazine. This is the paper that triggered all the hype around reinforcement learning in the last decade. This is basically a deep learning formulation of the Q-learning algorithm I've just shown you. So if we knew the optimal value function, we would also know the optimal policy. The challenge is that value functions are typically complicated and very noisy. On top of that, if the state space is very large, the tabular method I showed you before does not work. So the table I show you is not applicable to most problems because they are just too large. You don't have enough memory in a computer to store such a large table. So what the DQN algorithm does is to replace this table by a neural network. And it uses this network as a function approximator to the Q function. This network is once again randomly initialized and is updated iteratively through experience by interacting with the environment. And it has been proven that the optimal Q values obey the Bellman equation. So you can actually, by updating regularly this network, the parameters of this network, is proven to show that it converges once again to the same values as the original Q learning. One important feature of the DQN algorithm is the so-called experience replay. Now, these networks are trained using gradient descent. And one requirement of gradient descent algorithms is that the samples need to be IID. That's independent and identically distributed. You don't always have this with reinforcement learning. In Markov decision processes, the samples between state transitions, between consecutive state transitions, are highly correlated. This correlation breaks the IID requirement of gradient descent. So if you just try to apply online gradient descent when training this network, this will not converge. That's why experience replay was a very important insight of the DQN paper. What they do is basically, as an agent interacts with the environment, they collect the so-called state transition. This is, for instance, one state transition. To bring in an original state, you take an action, receive a reward, and arrive at new state. This is one transition. So what DQN does is to store these transitions in memory. And once you have a lot of them, and I'm talking about tens of thousands, you just sample randomly from this to create a batch of transitions, typically batch size is 32 or 64 transitions. And this is the batch that you use for training. Now you have transitions that are not consecutive and therefore are not highly correlated. And this does not break the IID requirement of gradient descent anymore, which allows it to converge. And this is the technique that was used to beat the Atari testbed a few years back. Okay, so as I said, this was the paper that started all the hype around machine learning, but that's why it's also important to stop and think before applying it everywhere. Just remember that reinforcement learning is a technique that is designed to tackle sequential decision-making problems. For instance, problems in radio resource management. Those are problems where you could apply reinforcement learning. So basically, reinforcement learning is promising for problems where you have a lot of data, like one, two, where you have many inputs. Think of scheduling, MIMO. It's also interesting if you have some sort of simulated environment or an environment that is shielded and cabled, because then you can just train your algorithm on the simulated environment and then deploy it in the field in sort of a warm start. But it's always important that you can formulate your problem as a Markov decision process. It has to be a sequential decision-making problem. Also, problems where the rewards are delayed are good candidates for reinforcement learning. Think of, I don't know, power control decisions. You take a decision regarding transmission power, but you don't know until a few milliseconds later whether you have cross interference or not to the neighboring cells. So that's what we call a delayed reward. And those are also good candidates for reinforcement learning algorithms. Now, situations where you don't need reinforcement learning. If you really have an efficient implementation, like, I don't know, digital filters or fast Fourier transforms. They're cheap, they work well, they're fast. You don't need reinforcement learning for this. Also, if you don't have enough data, I'm thinking of things like network blackouts. Yes, they happen, but they don't occur every day. So it's going to be difficult to collect a large data set for such problems. And if you already have a very good intuitive modeling, then you might do without reinforcement learning. Okay, so much for the basics. And now I want to show you an example of a very well-known problem in telecommunications that can be solved using machine learning techniques, more concretely using reinforcement learning. And this is a problem. I want to show you a problem that I used recently in a competition of machine learning for communications, where various teams proposed various solutions to this problem. So this problem is very well known. Okay, so think of it as the well-known time frequency radio resource allocation problem. So here we have a large environment, maybe 1 square kilometer in size, with one base station at the center and some UEs scattered randomly across the environment. These UEs, they move also at pedestrian speeds in rectilinear trajectories in random directions, and they bounce off the edges. The objective here is for the base station to deliver traffic to the UEs. Okay, so the base station receives traffic from the cloud in the form of PDUs, that's protocol data units, and it's the job of the base station to allocate the radio resources to the UEs such that they receive their expected traffic according to the traffic requirements. And we have a list of different traffic profiles. By the way, these traffic profiles have been extracted from the 5G NR specification, so they are not completely arbitrary. And you see that some UEs with a traffic profile of 0 can be doing just web browsing, other ones are doing voice, other ones may be streaming video, and depending on what they're doing, they will have different bit rate requirements as well as different delayed budget requirements. And here I'm also illustrating the transmission buffer that the station has. Okay, so for each UE, there's a number of PDUs in the buffer. For instance, in this case, for the first UE, we have 3 PDUs waiting in the buffer to be transmitted. Just one PDU for second UE, and so it goes. So once again, the base station needs to allocate radio resources to the UEs such that the transmission of these PDUs is possible. This is a time frequency or TMA resource allocation problem. We have time frequency resources that need to be allocated to the users. And we formulated this as a micro-precision process such that at every time step, one resource block needs to be allocated. So if you see here at the lower left, that I've replaced the word agent by an icon of a base station. So it's actually the base station, in particular the scheduler of the base station, taking decisions every time step. So every time step, the base station receives a state measurement that describes the channel quality indicator of the UEs, the buffer occupancy, that's how many PDUs are there to be transmitted, how long those PDUs have been waiting in the buffer to be transmitted, the quality of service identified classes, those are the traffic profiles of the UEs, and also an indicator of what is the current frequency resource that needs to be allocated. And again, on every time step, the base station just chooses one UE to get allocated one resource. So on the first time step, we allocate this resource to the green UE. Then we allocate the second resource to the green UE. So we go. Sometimes we allocate other UEs. And this is the sequential decision-making process that the base station needs to do. Okay. So when do we evaluate whether this allocation has been good or bad? In other words, when do we provide the reward? We only evaluate the performance after a large number of time steps. This is to avoid noise in the reward. If we computed this every time step, the reward will be varying widely and it will be more difficult to converge. So that's why we only evaluate it after, say, 200 or 300 time steps. And how do we evaluate it? What is the reward function? In reinforcement learning, it's typically difficult to design a reward function. This is something that requires a lot of trial and error. In this particular problem, the reward is very simple, I think. It's just a negative sum of buffer sizes. All right, so the more data left to transmit, the less reward one gets. On every time step, we provide a reward of 0, except on this evaluating time step I mentioned before, which is when we calculate this reward function. And you see here on the right that PDUs that correspond to non-GBR traffic are penalized twice. Okay, that's just to motivate the agents to send this traffic as fast as possible, but with no concrete GBR requirements. GBR, by the way, stands for guaranteed bit rate. And there's no need to explicitly penalize GBR bit rates because the buffers fill up at a constant rate depending on the data model, on the traffic data model. Okay, so this was the problem formulation. Let's recap a bit. What do we know about this problem? Well, first of all, we have perfect information. I mean, if you were to build an expert scheduler, like a round robin or a proportional fair scheduler, the state contains all the information that you need to solve this problem. There's no information missing. The transitions are stochastic, meaning that there is some randomness in this problem, right? We don't know when the traffic is going to arrive. This is random. We don't know how the UEs are going to move, in which direction they're going to move, which has an impact on the variations on the channel. This problem has the Markovian property. This is maybe not completely realistic. In fact, this is sort of an abstraction for simplicity. As I said already, real radio channels do have a time correlation over time. So that's not the case in this artificial problem. But again, this is just for simplicity in this machine learning competition. This is a problem with delayed rewards, but at least we know the periodicity with which we should expect rewards to arrive. And then we also have some domain-specific knowledge. Okay, we know the traffic models of the UEs, we know the reward function, and this is information that you could exploit if you were to write an expert scheduler. You will need to add weights, and this knowledge could be used to design your weights. Okay, so here I'm showing you the performance of some schedulers on this problem. Okay, and what I'm showing you here is the reward average over 16 episodes, and I'm just plotting only the final step of each episode because the reward at all other steps is 0. We're just evaluating the reward at the very end. So you see here the lower lines, that's the blue and the green lines, they correspond to a random scheduler and to a round robin scheduler. So the random scheduler is it's just a scheduler that takes on every time step random decisions. Okay, it just chooses a UE randomly, disregarding completely the state information it receives from the environment. And as you may imagine, this is not a very good idea. This is not a very good policy because the transmission buffers fill up very quickly. And this you can see by the reward decreasing. Since the reward is the negative of the occupancy in the transmission buffers, then it's only normal that the reward decreases until the buffer is full. Then it's not like the round robin scheduler is performing any better. The round robin scheduler is also just allocating resources in sequence, UEs in sequence, and it performs pretty much as badly as the random scheduler. Then we have introduced a very small condition in the round robin scheduler where we only allocate a user if there is traffic for the user. If not, we skip to the next user with traffic. And this provides significant gains. As you see here, the purple line, which is high at the top, is the one that performs the best. We have also included a proportional fair scheduler that performs not as good as the round-robin if traffic scheduler, but that's just because the proportional fair scheduler has not been optimized. Typically, in proportional fair schedulers, you have weights assigned to different criteria, but this was not the case for this scheduler. Here assuming the performances delivered by this round-robin if traffic and proportional fair scheduler. And here I show you the performance of the team that won the competition. That's team 3. And you see that this team performs a lot better than the round-robin conditional traffic. Now, this was a competition that we carry out in the framework of another European project called Project Windmill. I cannot give you details about how this team actually achieved this performance. I believe they want to publish it, so I should shut up. But all you can know right now is that it is possible to write a machine learning solution to this problem and perform optimally. I can mention that this team used the approach of this team involves some sort of evolution strategies, but that's as far as I can go. If you want to try yourself, and I highly encourage you to do so, we have open sourced this problem. It's available on GitHub for everybody to use. I believe this is a pretty good entry point to use machine learning for communications. And the code is, I hope, well documented, so there are no changes needed to run the default simulations. And we've also included the default agents, which you can use as templates for your own solutions. So I really encourage you all to use it. If you come up with an intelligent solution, you can publish it. Just remember to add a reference to this project. You're more than welcome to contribute to it as well. I've described to you this resource allocation problem, but our ambition is to expand this suite of problems with more problems in wireless communications. So if you're working on NOMA or MIMO or URLC, feel free to add them here. And I think it's also fun to compete. I mean, we know that the current best performance is -1503, as I've written here. That's the performance of the team that won the previous competition. If you find a solution and if you can perform better, then make sure to add your achievements in the leaderboard in the GitHub website. Okay, so now I want to show you yet another problem in telecommunications where you could actually use machine learning techniques to solve it. And this problem is uplink power control. It's again a well-known problem, which is precisely why it has value as a didactic tool to learn machine learning. Power control is basically a feature of the base station, which the base station uses to manage the power with which the user equipment transmits in the uplink. And there are many reasons why we want to do that. As you may imagine, the UEs transmit with too much power, they will suffer from a higher battery drain. In 3G, for instance, there's another problem which is called the party effect, which basically means that all the users try to transmit with a power higher than the other ones. And at the end of the day, they all just transmitting at maximum power and nobody can hear anything. One reason to have power control in 4G and in 5G is to control the so-called peak to average power ratio. So if the transmissions of two UEs reach a 5G base station with different powers, then you have what we call non-flat, so spectrum non-flatness. You don't achieve spectral flatness. And this translates in the time domain as a high peak to average power ratio, which causes problems in the modulation. And on top of that, if users transmit with much power that they actually need, they may cause high interference to their neighboring cells. If on the other hand, users transmit with too little power, well, they will have a lower bit rate and worse connectivity losses. So the bottom line is that power needs to be controlled. And this is controlled by the network, it's controlled by the base station. And typically there are two categories of power control algorithms. We have open loop power control and closed loop. With open loop power control algorithms, it is the UE the one who calculates its transmit power on its own, respects the parameters provided by the network, but those parameters are sent just one time only, and then it's up to the UE to use them to configure their power. And then we have closed loop power control algorithms that try to address fast changes in the channel. And typically the base station would send power control commands very fast to the UEs, typically every millisecond, trying to address that. Now the details of a power control algorithm depend on the technology that we're using. For instance, in 3G, the objective of closed loop power control is to keep a good signal to noise ratio for all UEs. And on the other hand, on 4G and 5G, closed loop power control is all about keeping the receive power of the UEs around the OLTC operating points, which is to achieve this spectral flightness I mentioned before. So the details depend a bit on the physical layer technology that we're using. So I've recreated a power control problem in a Jupyter notebook, which I'm going to show you in a moment. This problem is a bit similar to the outer loop power control of 3G. I've implemented this using OpenAI Gym. I'm not sure if everybody knows this, but OpenAI Gym is basically the Python API of reference for reinforcement learning problems. So if you want to work with reinforcement learning, you should totally know or be familiar with OpenAI Gym. Make sure to check it out. So in this problem, you're playing the role of the station MAC layer, and your job is basically to send transmit power control commands to the UE. That can be commands to reduce the transmit power, to increase it, or to leave it constant. You can increase it by 1 dB or by 3 dBs. And the objective is to achieve a constant SNR target at the base station. Now the UEs are obviously moving, and we don't know beforehand where they're going to be moving to. So the channel is changing. That's why the base station needs to plan a bit in advance when sending those power control commands. And the reward we provide the base station is 0 if the SNR is close to the target, and -1 otherwise. So I'm going to show you the code in this Python node. Can someone confirm that you're seeing my browser window now?
Yeah, we can.
Okay. All right. So this is a Python notebook. I don't really like Python notebooks, but everybody in machine learning seems to be using them all the time, so I thought it would be maybe easier for everyone to read the code here. Okay, so it's a code that is again open source. It's available on Google Colab. So I've included a link in the slides, so you can all access it freely and run it. If you don't change anything of this code, the code will run smoothly. But of course, feel free to play around with it, change the parameters, and so on. So I'm going to explain to you the different parts of it. I think this part is pretty clear. It's just a set of imports that we need, some libraries that we need and we'll be using later. Then we have the system parameters. We want to execute around 500 episodes. And each episode has a maximum of 500 steps. And this is the signal to noise ratio target. The objective is to have 4 dBs of signal to noise ratio at the UE. By the way, this is an environment with just one UE. And this is a form of randomness. This is just to make sure that every time you run it, you will get the same result. Of course, going forward, you will want to change this and run it several times for statistical reasons. These are just some initialization functions. We just allocate some memory to the rewards I want to be collecting for each episode. And here we seed the simulation. Okay, this is the main class that implements the problem. Okay, it's called an Uplink Power Control class, and as you see, it inherits from this OpenAI Gym environment. If you never use OpenAI Gym, you should have a look at it. But the code is nevertheless very small. So here you see I define some basic parameters like the position of the base station in the XY coordinates, the initial transmission power of the UE, 3 dBms, the speed of the UE, and the time between time steps in milliseconds. You can change all this at no harm and just see how well the algorithm performs in different circumstances. Okay, I've added here some documentation for you to read. These are the actions that the agent needs to take. There are 4 possible actions on each time step to decrease, maintain, or increase the transmit power. And then if I go just down here, this is the step function. This is the function that is executed when on every time step when the agent, in the base station in this case, selects an action. You see that's what we do when the base station selects an action. We do some checks to make sure that the action is within range. Then we just update the position of the UE. Once the UE has a new position, we update its transmit power depending on the action on the base station. We recalculate the signal to noise ratio, and then we calculate the reward. And the reward is, as I said, 0 if the SNR is close to the target, and by close I mean within 1 dB. Otherwise, it's -1. And that's it. There's no more code to that. I mean, this calculation of the SNR is trivial. It's just a helper function. But that's basically the implementation of the problem. Here we have a class that implements the solution to the problem. It implements the solution by using Q-learning. If you remember the Q-learning algorithm I presented to you a few slides back. This algorithm has a policy, which is typical Q-learning policy, which means that we calculate the Q values stored in this table for all the possible actions. So we enter this table with the state, that's the current state, and we obtain a vector with the Q values for all the possible actions. Then we just choose the best action, and that's the action that we're going to be executing. Okay. So here we're just instantiating this agent. I'm going superficially over the way, but it's probably better if you spend 5 minutes just reading it. I think it's small enough for you to be able to understand it within, I don't know, half an hour. And then we find the simulation loop. Basically, this is the code that runs 1 episode where we execute the agent environment interaction. So basically, here's where we take a step. So here, the agent applies the policy to obtain the probabilities of the different actions. It just chooses the action with the highest probability, and then we invoke the step function of the environment to execute it. And this returns, of course, a new state at work, and it tells us whether the episode is finished. And then we just collect here the KPIs on the performance. And it's just a wrap up to the previous run episode function, just to execute it several times. Okay, so now to the results. I ran here 500 episodes. I believe this num episodes variable is set at the beginning. And here I've plotted the results. Okay, here you see the green line shows you the reward per episode. Here are the 500 episodes I've simulated. And you see that the longer it trains, the higher the reward gets. Now this reward is pretty noisy, so it's hard to conclude whether we were just lucky perhaps. That's why I've later repeated this with different random seeds and computed an average. Now, what I'm showing in this other graph here below is the SNR for some episodes. You see that in the first episode, episode 0, the SNR is pretty much all the time at 20 dBs, which is a lot far away from the target of 4 dBs. This will be equivalent to these episodes right here at the very beginning of the training session. But as training progresses, the SNR decreases very rapidly to the target of 4 dBs. That's because the base station has realized the situation and it has learned to reduce the power of the SNR. Of course, there are glitches. Sometimes this SNR increases or decreases, but that's just because the UE is moving So the basic station needs to react and correct transmit power depending on the circumstances. As I said, you can run this for different seeds and then compute an average, as I've done here with this mean. This will give you a less noisier evolution of the reward. You see now that this is the average over 32 different simulations, and you see that the average reward increases until almost 0, which would be the optimal reward in this case. I've talked about the learning rate in many occasions, and I said it's important for convergence. So what I've done, if I simulated once again the same problem with a different learning rate, just for you to compare. So here's the whole simulation running, and here is compare. So you see that the red line converges a lot faster than the green one, and the red line is actually for a smaller learning rate than the learning rate of 1. That's because if your learning rate is too high, you have a risk that your cost function maybe that you will be bouncing off the walls of a valley in the cost function landscape. So that's why the optimization of the learning rate is important for rapid convergence and for convergence warranties as well. Okay, so maybe considering the time, I think it might be a good time now for questions. Roberto, Christos, not sure what you think.
Yeah. If you want to take a few more minutes and finish, I think we are fine. But yeah, if you're done, we can open the question. Yes.
I have like 30 more slides. I don't think it makes sense to go into
No, 30 more slides. No.
So let's go with the questions.
Okay. Yeah, there are already a few questions on the pipeline. So I try to enable the audio for the students, for the people connected, such that they can. So, Wasem, are you connected? Can you listen?
Yes. Can you hear me?
Hi. Yeah.
Hi.
So yeah, please go ahead. You can ask your question.
Yes. Well, thank you so much really for this. So it's very useful and interesting. My question in the slide was the CQI, channel quality indicator. So in that slide, I can see there are many parameters, and we're trying to do is basically to optimize. Considering a real situation in a Mac layer, are we trying to increase to optimize to get a faster system that give us faster and accurate decision, or we just trying to replace it in this situation? If that's clear.
I'm trying to the question. Which slide do you mean? At the very beginning in supervised?
Yes, in the supervised learning. So,
okay.
So it seems to me it looks more like so these indicators are more or less given to the these indicators are actually given in the MAC layer, so they can make a decision on the rate of the transmission between the receiver, right?
Okay. Right.
So my question is, are we trying to increase the speed or trying to increase the accuracy of getting the right rate between the transmitter and receiver? Sorry, let me just continue the second part. Maybe they are connected. And the second part is, should we do this at the transmitter? So basically, we will enhance the or reduce the acknowledgement process, and we enhance the rate, or we should put it at the receiver side, and that's why the acknowledgement will be very accurate.
Okay. Yeah. I think I can answer both questions in one go. This is a very simplistic example. It's not simpler than that. This is just a prediction problem. Okay. So what we want to do is see if given all of these parameters we can predict the number on the right. That's what it is. And this is something that you will want to do most likely at for instance, in a cellular system at the base station. Okay, and in the base station you will perform this prediction for both the uplink or for the downlink. But the idea is to find if you can actually predict the data rate that the user is going to obtain for a given set of parameters, then you could actually choose these parameters optimally. Think of it as performing some sort of exhaustive search. You could obtain this prediction for all the possible combination of parameters, and then you will just choose the combination that yields the highest data rate. And this will tell you automatically how many resource blocks you need, how many TTIs, state transmitters should be allowed to go on for, and many other pointers. Of course, it doesn't let you choose the rank indicator because this is a measurement of the UE. And it doesn't let you choose the CQI. This is given by the channel. But it lets you configure all the parameters given the circumstances. But again, this was just an example I used to show you how you could actually predict quantities given as a sequence of inputs. Whether you use that for scheduling later or for other purposes, that's really up to the manufacturer.
Any other question, Mazen?
Oh no, thank you. That's but would it be more accurate or more sense if we try? I understand this is not only an example. If we try to implement such a thing, would it make sense if we try to implement this at the transmitter, or we try to put it at the receiver?
I don't see why you would want to do that at the receiver. At the receiver, you can measure the data rate. You don't need to predict it beforehand.
So, because the receiver is the one who is actually affected by the rate, and because the transmitter doesn't know what should be the right rate or what is the channel situation at the receiver side, but the receiver side who actually knows what is the situation in the SNR level and interference, and that's why you have the acknowledgement to process. So if the receiver, so if, are we trying? I mean, I understand if this. Perfect if we can do it at the transmitter side, but if the transmitter side knows all the parameters of what's going on at the receiver.
Well, there's usually a feedback. I mean, most communication systems have a feedback. So the receiver takes measurements on the channel. The CQI is reported. The CQI is measured at the receiver side and fed back to the transmitter.
Okay,
of course, there's a delay, but all this information is usually available at the transmitter side. And it's up to the transmitter side to configure the other parameters.
Okay, yeah, thank you. So basically, we still need the feedback in that case.
Yes.
Okay. Yeah, thanks so much.
Okay, there was another question in the queue from Ahmad. Ahmad, are you able to connect with the microphone? Yeah, I can see you, so you can unmute now. Yeah. Hello? Ahmad? No? Okay.
I don't hear it.
Yeah, so I'll ask the question for Ahmad. I don't know. So Ahmad was asking that for a ML-based modulation scheme classifier in a fading channel, how to consider applying such system in low latency application? And then he was also asking, for a block fading channel, is it the case where we need to train the ML system for every channel realization?
Well, it depends on the machine learning system that you're using. As I said already several times, the more data you have usually correlates with high performance. So certainly the more channel realizations you have, the more generalizable your trained model is going to be. But there's usually, in machine learning algorithms, there's this conflict between bias and variance. So, which basically means that you typically want a model that has a low bias, which means that it has a low error. But this means usually that your model, if you have a low bias, you have a high variance, which means that the moment you change your data, you want to have a different model. So if you try to train a model with many channel realizations, you may end up with a high bias because it's going to be very difficult to have it perform optimally in all of those. But yeah, of course, it depends on the details. I mean, I think the question is too generic. And what was the first question again? Can you repeat it, Jonas?
Yes. So the first question was about if you use an ML-based modulation scheme classifier in a fading channel, how to consider applying such system in low latency application. So I don't know what he wants to ask, but I think he's asking like how can we apply in low latency application this ML-based modulation scheme, for example, the selection of the modulation scheme I think in your application you were not targeting low latency
yeah,
application, right?
Yeah, I'm not sure I'm the most able person to respond to physically your questions. But in any case, what I can tell you is it all depends on how you model your problem. I mean, if you have a problem where you want to select the moderation encoding scheme, this is a labeling problem. Okay, there are usually a handful of MCS schemes you can choose from. So if you can model your problem as a labeling problem, you will have some, just like I have here in supervised learning, that's a supervised learning problem. Okay, you're going to find the values on the column to the right. In your case, those are labels. It could be moderation encoding schemes. If you can formulate your problem such that that's what you want to predict, what you need to do is to collect the data and run some sort of supervised learning algorithm. But yeah, again, the devil is in the details. So sounds easy on the surface, but then you have to configure your hyperparameters and so on. So, but it's all about the formulation. You need to formulate your problem properly in a machine learning framework.
Yeah, there is a last question that, well, I think it's clear, but is asking if it's possible to get the code for further research. I think you mentioned already that there are available code in the online, so perhaps you can just.
The only code I can share with you is the one I've linked. The wireless suits project is on GitHub, available to everybody, and I'm aware of people working worldwide on it. And there's also this notebook I've just shared, which is mostly for didactic purposes. So you can also use it for sure. That's one's available. And the links are in the slides. I think you will provide the slides to everybody.
Yes, we will share after the ending of this day. Yeah. Okay, if I can make a final remark, I think is, I mean, in the presentation of Alvaro, he made some interesting point, and the first one is about not applying machine learning in any type of problem, but just apply machine learning when you need machine learning, right? So nowadays, since this topic is becoming very hot, there is the tendency of applying machine learning everywhere, which is not the right thing to do. And the second thing is, as well, I think it was very interesting, your presentation that you made is how you select the right tool for the problem that you want to solve. So this is another important aspect, because sometimes if you select the wrong tool, so you will not get the answer to your problem. So this are two things that I think for people that are involved in research, especially machine learning applied to telecommunication, they really need to consider what is really useful and how, and if you really need to apply machine learning. Okay, Christos, do you have any question, or we close here?
I think we're good to close.
Yeah.
Thanks again, Alvaro, from my side as well.
Yeah.
Thank you all for inviting me.
Yeah, thanks a lot, Alvaro. This was a really interesting seminar. Yeah, thanks a lot for participating, and thanks a lot.
And we're going to continue in a minute. So we'll take a coffee break or a poster break for 20 minutes or so, and we're going to carry on with the next talk on model-aided machine learning from Marco Di Renzo. So let's take 20 minutes, and let's come